Okay, so the next thing that we want to do is find how to determine the equation for a tangent plane to a parametric surface at a given point. We found tangent planes for surfaces all the way back in chapter 14, when that surface was it was the graph of a function of two variables, but we haven't looked at it from the perspective of parametric surfaces. So a lot of the ideas are kind of similar. Remember, in order to find the equation of a plane at all, you need a normal vector and a point on that plane. So the work that we're going to put into this is going to be the work that we need to do. What we're going to develop here is a method for finding that normal vector. So let's suppose we have a surface S, and it's given this parametrization. What we're going to do is start by looking at the grid curves for this surface by holding u and v constant. So for example, if I were to hold u constant, let's say that u is equal to u naught, then this parametrization, if I plug that constant in for u, the only variable now would be v. So that would mean that this parametrization determines a grid curve on S. It determines a curve, and I'm going to call that C1. We can see that here. So down here is the UV plane, where I'm picking points to plug into my parametrization to give me this surface here. And if I hold U constant, that's going to correspond to this line right here. And then if I were to basically find the image of this line on this surface here, it would give me this curve C1, which is on that surface. Then what I would want to do is find the tangent vector to that curve. Well, in order to find a tangent vector, if we have the equation for a space curve, we know that we take its derivative with respect to whatever that variable is. And again, the parametrization after plugging a u in for constant uses only v as the variable. So that means if I wanted the tangent vector to that curve C1 at that point P naught, then I'm differentiating my parametrization for that curve with respect to v, giving me this. Notice all the partial derivatives are with respect to v here. Okay, I want to repeat that process, but instead of holding u constant, I want to hold v constant. So if I were to do that, following similar logic, I'd get a second grid curve, C2, and a tangent vector to C2 is going to be given by the partial derivative of, the derivative of that vector function with respect to u. Now, by holding u constant and getting this vertical line here, and holding v constant and getting this horizontal line here, they intersect at a point which, when plugged into my my vector function, is going to give me this point P naught. And here are the two tangent vectors that we just came up with. I know that if I were to find if I want the tangent plane to this surface at that point, I could see that the tangent plane would contain these two tangent vectors. So really what it boils down to is finding the equation of a plane containing two non-parallel vectors. We know that in order to do that, you compute a normal vector by taking the cross product of these two, which we describe here. This shouldn't include those magnitude or absolute value symbols. It's just R of u cross RV. That's going to give me a normal vector, and then I find the equation of a plane using the normal, or using the usual method, the normal vector with the point that we were given. So I'll use an example to make this a little more concrete. Little terminology. In order to do this at all, the cross product has to give us an actual vector with direction, which means it can't be the zero vector. So surfaces that have tangent planes like this are called smooth, and those are surfaces where RU cross RV is never equal to the zero vector. If it was, that would correspond to weird little things like corners and cusps and stuff like that in the or ridges and things like that in the plane itself. So let's look for a tangent plane to a surface that's given by this parametric function here. So R of uv is equal to u squared plus 1 I plus v cubed plus 1 j plus u plus v k at the point 5, 2, 3. Now, before I find those vectors ru and rv, This point is the result of plugging in a particular value for u and a particular value for v into my parametrization. That's what would give me a point on that curve, on that surface. So I need to determine what are the values of u and v that could be plugged into this parametrization that would result in this point. And it doesn't take too much work to see that the point u naught v naught that's going to give me the point p naught on the surface is the point 2, 1. I can verify this by setting 5 equal to u squared plus 1, solving for u. I would see that u is equal to plus or minus 2. Same thing here. If I set v cubed plus 1 equal to 2 and solve for v, I would see that v is equal to 1. The sum of u and v has to equal 3, so that narrows this down to a positive 2 for u, 2 and 1. You can write that down as a system of equations if you want. A lot of the time, it's just easier to find this by inspection like we just did. So now what we need is RU, and remember RU is the derivative of this function, this vector function with respect to u. So I would get 2u for my I component, 0 for my j component because there are no u's here, and then 1 for my k component, so plus k. RV, I do similarly. Notice this time my I component is 0. My j component would be 3v squared. And my k component would once again be 1. So that means if I want to find the cross product of these two vectors, I, j, k, then I'm using my components. It's 2u. 0 is my j component here. Then 1. Then I have 0, 3v squared, 1. Now you can evaluate this determinant as is, but remember we have values for u and v, so we might as well just plug them in at this point. That's going to give me the determinant. 2 times u, that'd be 2 times 2. That's what I have there. 4, 0, 1. 0, v is equal to 1, so 3v squared would be 3. And evaluating this determinant gives me negative 3i minus 4j plus 12k. That's the normal vector for my tangent plane. Okay, remember for the equation of a plane, you need a normal vector and you need a point in the plane, which we're given right here, 5, 2, 3. So that means the equation of my plane is going to be negative 3 x minus 5 minus 4 y, what was my y coordinate? 2, y minus 2, plus 12 z minus 3 equals 0. And I'm fine leaving the equation of the plane in that form, but if you wanted, you could distribute those in. You can multiply by a negative to make this first coefficient positive. It doesn't really matter. I'm just going to leave it in this form. Okay, so that should feel somewhat familiar because it uses the same machinery that we've used for finding equations of planes in the past. Now let's move on to surface area. Back in chapter 15, we talked about how to find the find the area of a surface when that surface is given by a function, z equals f of x, y. We want to find the area of surfaces that are given parametrically. This allows us to find surface areas for surfaces that aren't necessarily the graphs of functions. So suppose we have a parametrization for a surface S, R of uv, and for the sake of this argument, we're going to say that uv is restricted to lie in a rectangle D. Turns out that we can be more general than this, but this just helps with this initial argument. What we're going to do is treat this the same way that we treated double integrals when we first derived them. We're going to take that rectangle and cut it up into sub-rectangles, which I'm going to call Rij. The image of each one of those sub-rectangles in D is going to correspond, once it's plugged into our parametrization, to what we call a patch of the surface S. And I'm going to call that patch Sij. Here's a picture to illustrate what I'm talking about. So here is the UV plane. This is where we pick our parameters U and V. And we're going to restrict our parameter intervals to lie within this rectangle. The dimensions of any given subrectangle are going to be delta U, delta V, just like when we did double integrals. The image of one of these rectangles corresponds to one of these little pieces of the surface, and we call these patches. I'm also going to select the point in the bottom left-hand corner of any one of these subrectangles and notate those UI star, VJ star, because we're going to use those points in our parametrization. So this argument is going to look really, really similar to arguments that we've seen back in chapter 15, when we talk about double integrals and the Jacobian and things of that nature. The goal here is to approximate the area of the little patch, Sij, which we would get, this is like a blown up version of that. We're going to approximate it with the area of a parallelogram. And the way that we do that is just like what we did before. We find these two curves on the boundary of Sij and compute the tangent vectors to those curves at the point Pij, the lower left-hand corner. Pij is the image of the point UI star, VI star, or VJ star, that we mentioned up here. So if I compute those tangent vectors, I then have to scale them appropriately so that this rectangle is not huge, or this parallelogram is not huge. It needs to be a good approximation for that rectangle. We can get that by multiplying RV star, that would be the tangent vector here, by delta V, which is, remember, that's the length, or that's the height of this subrectangle up here. Multiply RU star by delta U, that's the base of this little subrectangle here. That scales the parallelogram down to an appropriate size. We went into a more in-depth argument in chapter 15 for why these scalars are the way that they are. They came from the difference quotient that we used to approximate our tangent vectors, but so this is basically the same idea as what we've already done. To compute the area of this parallelogram, we know that the area of a parallelogram determined by two non-parallel vectors is just the magnitude of their cross product, which is given here. Using properties of magnitudes and cross products, I can pull the two scalars out, and I end up with this. Okay, so the approximation of the area of our entire surface would just be the sum of all the approximations for the areas of those patches, which is given in the form of this double sum right here. Naturally, if you take a limit as m and n here go to infinity, this turns into an integral, and that integral we expect will give us the actual area of that surface. So all of that was to lead to this formula, which will give us the area of a parametric surface. If you have a smooth parametric surface S, and it's given by this equation, this parametric equation, and if we assume S is covered just once as U and V ranges throughout the parameter domain D, to give you an analogy to make sense of this, when you talk about parametrizing curves back in algebra and trigonometry, we mention how you have to be careful about how you choose your parameter interval because you might end up traversing a curve more than once. For example, if you look at the parametrization for a unit circle, x equals cosine of t, y equals sine of t. Normally we say let t be, let the interval that we define t in to be 0 to 2 pi. Well, that means the parametrization would traverse this curve exactly one time. If I made this 4 pi, then we would be traversing the curve twice. So we need to make sure that the interval here is chosen, or the rectangle here is chosen in such a way that we don't double up on our surface. You're generally not going to have to worry about that in this class, but it's something that needs to be mentioned at least. The area of that surface is given by this double integral, which comes from our derivation up there. So notice it's the double integral over the region D. It's a rectangle here, but we can actually generalize this to other regions, not just rectangles. Of the magnitude of the cross product of RU with RV dA. And RU and RV are given here. These are just the derivatives, partial derivatives of this vector function with respect to U or with respect to V. So, getting close to wrapping this section up, let's do an example where we find the area of a parametric surface. This one is going to be the area of the helicoid that we found back in the beginning of this section, the one that we graphed. We want to find the area of this helicoid given by this parametric function, where u goes from 0 to 1, v goes from 0 to pi. Okay, so the first thing that we're gonna need to do is determine what RU and RV are, because we need to take their cross product. RU is the partial derivative of this with respect to u. That's going to give me cosine of v I plus sine of v j plus, if we're differentiating with respect to u, then v would be held constant, so this is the k component is actually 0. So I actually don't even need to write anything. I'll just leave it like that. Okay, and then my RV, if I differentiate with respect to v, I'm going to get negative u sine of v I plus u cosine of v j, and this time I get a 1 for my k component, so plus k. Now we need the cross product of those two vectors, I, j, k. I have a cosine v, sine v, and 0 here. Negative u sine of v, u cosine of v, 1 here. Okay. Evaluating this cross product, you're going to get sine of v as your I component minus cosine of v as your j component. I skip all of the work, working out the little cofactors of this thing, because I know you should be able to do that by now. Notice what my third, or my j component looks like. U cosine squared of v plus u sine squared of v. We know that you could factor the u out, and then the cosine squared plus sine squared is just 1. So this can be written this way: sine of v I minus cosine of v j plus u k. So now what we need is a magnitude cross. Okay, so that would be the square root of sine squared of of v plus negative cosine squared, but if I square it, the negative goes away, so it's really just plus cosine squared of v plus u squared, which we know that becomes 1. This simplifies to 1 plus u squared. So according to my surface area formula, the double integral that we want to evaluate is the double integral over the region D of what we just found, the square root of 1 plus u squared dA. Because my double integral was defined as a rectangle, it's very easy to turn this into an iterated integral. This becomes the integral from 0 to pi, integral from 0 to 1 of root 1 plus u squared du dv. Notice that I have a product of a function of u with a function of v, so I can bring the dv out. So here's my dv, 0 to 1, square root of 1 plus u squared du. Okay, this guy is easy to evaluate. That just comes out to pi. This guy is not easy to evaluate, but you can do it, and you probably did in Calculus 2. This is a classic trig sub. You would set u equal to tangent of theta. Du is going to be secant squared of theta. And then after using the trig identity here, you end up with a secant cubed of theta. Secant cubed is it's a classic example of trying to integrate that in Calculus 2. You use a kind of a somewhat clever application of integration by parts. It's a fairly lengthy integral to work out, though, and I'm not going to go through all the details here. So if you'd like to see a more lengthy derivation of that, you can ask in the discussions in Canvas, but that is something that hopefully you encountered back in Calculus 2. So if you evaluate this, the integral comes out to 1/2 times root 2 plus the natural log of 1 plus root 2. One more parenthesis in there. Okay? Not a pretty answer, but that's what it is. All right? So finally, and this is just something I'm going to mention because it's not really anything new. But back in chapter 15, we talked about surface areas for surfaces that are given as functions, z equals f of x, y. when we have those types of surfaces, we've seen this area formula before. But what I wanted to mention here is that this is what our surface area formula that we just came up with, which I'm looking for that page. This is what happens to this formula when we use, okay, where is it? Looking for my parametrization. Oh, there we go. It's what happens to this formula when we use this parametrization for our surface. Remember, if our surface is a function of x and y, we can use this parametrization. Notice that the I and j components are x and y. That gives a much simpler way of evaluating, that gives us a nice simple example of evaluating this cross product. I'm going to leave the details to you. You can either look at it in your book, or you can try deriving this on your own from our formula that we just came up with, but I'm not going to go through that here. It's fairly straightforward. Okay, that's it for parametric surfaces.